Hello everyone, welcome to this video. Here we will be introducing the Angular signals. I am Chuduman Namd and let's dive straight in. Now an Angular signal is a reactive value that wraps around a primitive that notifies interested consumers when its value changes. Signals can be of two types. They can be either be writable signals or read-only signals. Now let's look at writable signals. Writable signals are signals whose value can be changed, and also they can be created via the signal function. Now this signal function can be imported from the Angular / core module. Let's see how to create a writable signal. Now, first we import the signal function because it is exported from the Angular core module. Now, this signal is a function that creates a writable signal. Then, a writable signal is a signal whose value can be set or updated directly. Directly is the main difference between a writable signal and a computed or read-only signal, which we will come to that later. Now let's create a writable signal. First, we create a variable where we assign it to, then signal, and then the value. In this case, let's write 0. Now this creates a writable signal and assigns it to this counter variable. This counter variable is an instance of a writable signal. Now look at the value we passed here, 0. It becomes the initial value of this counter signal. Now mind you, a signal does not only take a number or a primitive. It takes other data types like object, arrays, dates. They can all be passed as the initial value of a signal. To read the value inside this signal, we need to call it. Now this returns the value inside this signal. Why do we have to call it? This is because signal returns a getter function. So this counter is a getter function. To understand this better, let's enter inside the Angular source code to see how this works. Now this is the Angular source code. We are inside the signal function to see how it works. Now you see when we call the signal function, it calls this create signal function and passes it the initial value that we called this signal function with. Now let's look inside the signal create signal function. Now you will see first it creates a signal node using object.create. We all know what this does. Now if you look at the signal node, you will see it's an object that has properties like equal value. So you see, if we don't assign or pass an initial value to the signal function, the value will be undefined. Now this equal is how it checks if the previous value and the current value when a signal is updated are the same, so as to re-render the component, but we'll come to this later. So you see it creates an object and then returns it. Now let's go back to our create signal function. So this is it. So this is an object, assigns it the initial value we sent it to. So it changes that initial value of undefined to the value it was passed into. Now it creates a function. This is a function whose name is getter. So you see it returns it. So this create signal returns a function. This is a function that is callable, and looking inside it, you see that it accessed the node value, which holds the initial value of our signal. Then it returns the getter function. So you see that this create signal returns a getter function. Now we go back to this create signal. You see now that getter function is held inside this variable signal function and it is being returned. So that's why this counter is a signal function which comes from this. So when we call this counter signal, we are calling this getter function so as to retrieve the value inside the signal. So this will give us 0. Let's log it. Now we have to run this with ts node. Now to reference where our Now you see it gives us the value 0. So you see this is how we read value inside a signal. Now to set a value directly to this counter signal, we use the set method. To do that, we'll call the set method like this, then pass in the value or the new value that we want to set directly on the counter signal, and it will notify any dependence on the counter signal. Now let's change the value from 0 to 90. Now this will change the value, set this counter signal. Now let's log it. Then in this statement, it will log 90 because this has directly set the new value there. Now let's run it. So you see our new signal after this line is 90. So this is how to set new value to a signal. Now we can also update a signal from the value of that signal or from the current value of that signal. This is done using the update method. How do we do it? We call counter dot update. Now this update takes a function. We call it an update function. Now this function will get the current value of the signal, and then we can now use it to make our computation to update the signal state or the signal value. Now this is the current value from this counter signal, and we can then now use it to update the value from this counter signal. And now this function also must return a value. The value returned from this function will be the update or the new value of this counter signal. Now let's update let's update this counter maybe to the double of it. Let's say the current value, and just times it by 2 so as to return the double of this counter, so that after this call here, now the counter value here will now be times 2 of 90 because the current value is 90. So the times 2 of 90 will now give us 180. So we will receive 180 here. So you see, now this update is also used to update the value of a counter. Now it takes, like we have seen, it takes an update function. This update function will return the value in which this update method will use to update the value of the signal in which it was called on. So here, and the function also expects the current value to be passed to it. Now it is not a must that we will use the current value, but what is noted is that it must return a function in which the current signal will be updated with. So we can just like return anything here. Maybe we can just return 24, and the value in this counter signal will be 24. So you see, so this update method is used if we want to update the counter signal from its current value. So that's the reason of using this. Or otherwise, you can simply use it without the value, or you can use the set method here. So in whichever case you use, both of them still works. So now we have seen what writable signals are in Angular. Very soon we will look into how to use this in an Angular application. As you can see, we are using it in a standalone JavaScript file just to demonstrate how it works. Now, in the next section, we are going to look at the computed signal or the read-only signal. Now, let's look at computed signals. Let's clear this. Computed signals are read-only signals whose values are derived from other signals. So you can see their values are dependent on other signals. Now, computed signals are created from the computed function. It is also exported from the Angular slash core module. So you can see computed. Now, let's see how we can create a computed signal. First, we will use our writable signal. Now, to create a computed signal, let's call this computed counter. Now, we call our computed function. Then, it takes a function as a parameter. Then, to derive its value, we need to call this signal inside it. Now, let's just return a double of it. So now this is now a computed signal or a read-only signal. Now looking at this computed counter signal, you see that it is dependent on this counter signal because it is used in its derivation function. So whenever this counter signal updates, now Angular marks this computed counter signal to be updated as well. Computed signals are both lazily evaluated and memoized. Memoized indicates that its initial value is cached and then the cached version is returned if the input does not change. Now, when we call this computed counter for the very first time, its derivation function will be run to calculate its value, which is 0 in this case. Now, this value returned will be cached so that when this signal is called again, the cached version of it is returned, skipping the recalculation. The recalculation means this derivation function will be called again to calculate its value. So this will not be called again on the second call and also on subsequent calls of it. This will not be called at all, only on its first time. Now, if this counter signal value updates or changes, we know that this counter signal is dependent on this computed signal. Now, if this updates, Angular will mark this computed counter signal to be updated as well, so that when it is called next time, its derivation function will be called to calculate its new value. So that's how computed counter signal works. It is both lazily evaluated and memoized. So this is done to speed up the performance of our computed signals, and also we can carry out computationally expensive functions such as filtering arrays. Now let's say 2 is here. Let's recap again. Let's say 2 is in this our counter signal. Then we call this computed counter. Now this derivation function will be run and it will return us 4. Now on subsequent calls of it, 4 will be returned because this counter value has not changed. So this is no longer evaluated, and after its first call, the value 4 is cached. And on this call, on this second call, this derivation function is not called. Even on subsequent calls, the derivation function is not called at all until the counter changes. Until the counter changes. Now, this counter changes. Not is it should not be computed. This counter changes. Now, after this call, Angular will mark this computed signal to be updated as well, or it will remove its cache. Just mark it to be updated. Yes, that's good. So that when it is called again, like this, its derivation function now will be called. It will not return from the cache because it has been invalidated, because the counter it depends on has been changed. So this derivation function will be called again. And in this case, because this counter will now be 3. So now it will return 6. Now on next call after this, it will return its value from cache. This derivation function will not be called. Its function will be returned from the cache. It will not be calculated from this derivation function. This derivation function will not be called. It will return from cache. Also on subsequent calls till when the counter is changed again, like this. The counter is changed again like this, maybe change to 10. So on next call of counter, then this derivation function will be called. So that's how computed signal works. They are internally optimized for high performance by Angular. Now let's test to prove that computed signals are lazily evaluated and memoized. Now to do that, we need to add a log here. Console.log to show that this computed counter was called. Yes, so for that, let's remove this remaining 3. Now when we run this, we will expect this to be logged only at the beginning of this. Then it will not log anything for this and this, because these two will just be gotten from the cache. Now let's set a mark here before we now change the state, the counter state. Now let's say let's rest here, so that we will now make a change, and then this, after this statement or after this counter update, then the next call on the computed counter signal will result in this being logged again. So in general, we'll expect only 3 logs. This at the beginning, then this log, then at here after the counter change. Now let's try it. So you see exactly only 3 logs. Now this computed counter came from this very first. After that, nothing was logged, because in this second 2 calls, the derivation function was no longer called. That's why we did not see any computed counter logs again. It only got the value from the cache of this and returned it. It did not recalculate again from this function. So that's why we had only 1 log. Then after and before this, let's rest here log. So you see, then after this log here, we updated the counter signal, and this counter signal then invalidated the cache on this computed counter, which made this call to call this derivation function to recompute the result, and then that's the reason why we saw this computed counter. Then after it, this one no longer logged this, because it will now pick the value after this call from the cache. So there was no longer second computed counter log here. So this is a proof to show you that computed signals are lazily evaluated and memoized. Now another thing we have to look at is that computed signals cannot be changed. So we cannot call the set function on it like this. We cannot call it. We cannot change it at all. They are only read only. So you see type error. Set is not a function. So we cannot update computed signals at all. We can't. Computed signal dependencies are dynamic. Now, when a signal is called in the derivation function of a computed signal, it becomes tracked. Now, there might be a case in which a tracked signal can become untracked. Now, let's see how that happens. Let's add a signal here. Let's say false. Now, we can use the value of this signal to know when to show a value or not. Now let's remove this. Now let's say show count. If show count is true, then we can return a counter. If not, we can just return true. Now see this case here. Now let's remove this so that we can explain this better. Now as you can see, we are having two signals inside the derivation function of this. Now when we call this computed counter signal first time, this runs and the value is false. Then it returns this. Now in this case, show count becomes a tracked signal of computed counter. So computed counter now depends on the value of this show count signal. Now see that this counter is called inside the derivation function of this computed counter, but it is not tracked because this code was not executed, so the counter was not called. So whenever a signal value is called, or a signal variable is called inside the derivation function, it becomes tracked. So in this case, when show count each value is false, it does not run this. So counter does not becomes a tracked value. So this computer counter does not track it, and this computed counter does not update when the counter value changes or updates. Now, if counter updates like this, the value of computed counter does not update. It does not recompute because counter is not tracked by computed counter. So you see, but if we update show count to true like this, now because show count is tracked by this computed counter, it will invalidate the computed counter cache, so that when we call the counter cache here, it will run this derivation function because its dependency show count value has been changed. Now in this case, show count now will be true and this block will be run. So when it is run, counter is run, its value is collected, which is 2, which is 90, times by this 180, it will be returned. So by calling this counter, counter and now show count will now become a dependency of this computed counter. So you see, it now becomes, both of them now becomes tracked by this computed counter, so that when the counter is updated, then the cache of this computed counter will be reinvalidated because it is dependent on this counter. Now, if we call this computed counter again, this derivation will be run and it will return 200 because counter has been updated. So this will now be 100 times to 200. It will now return. Now, if we change show count back to false and call this computed counter, now this will be run. And when we call this, it will invalidate the cache of computed counter because it is tracked by the show count. So when we call the computed counter again, this derivation will be run. And because show count is false, this will not be run again. It will only run this. And in doing so, this counter will become untracked. So that if we update counter again like this, it will not invalidate computed counter. So that when we call computed counter again, it will only return from the cache. So this will no longer have effect on computed counter again because of this was set here. So you see how dynamic dependencies of computed signals are. So this code already demonstrates how dynamic their nature is. So this the the dependency of counter to this only depends if show count is true. If show count is set to false, then counter is untracked. So that when its value is changed, it will not affect computed counter's cache. Only if this is changed. So if this is true, then show count and counter will not be dependent on computed counter. So that if either of them is changed, it will invalidate the computed counter cache. And this computed counter cache will be run when it is called again. So this is the dynamic nature of computed signal dependencies. Now we are going to see how to use signals in an Angular application. Now we have learned what Angular signals are. Now this is the time to see how we can use it in an Angular application. First, we have an Angular application here, which is a counter app that just renders a counter, and we can increment and decrement the counter values and also reset the counter value. Now we implemented this using the traditional way of doing this in an Angular. So which is just comprises of setting a state, then now modifying the state, and this modification of state causes re-render of the component. And look at here, we are using another component, which is the counter display, to pass in the counter, which is dedicated to rendering the counter state. Now let's look at the counter component. Now as you can see it is using the Angular at input decorator to grab the counter being passed to it and then render it in its template. So you can see it here. So whenever we change the state of the counter, then Angular knows that the value of this counter display component has changed. So it will render this counter display component to show the newest value or the current value of the counter value or the counter state. Now let's test our app. We'll click on increment. Yeah, the value updates. We click on decrement, it updates, and when we click on reset, it resets. So we see that this app is running. Now let's convert it to use the Angular signals. Now in this case, we are going to first create a file here. Now this file will hold our counter signal. We'll call it counter signal.ts. Now inside it, let's close this. Now inside it, we'll create the counter signal and then call the signal function, pass it an initial value of 0, and then export it. Now we're exporting so that other components can import and use it. Now we're assigning 0 to the signal function because coming to this counter, its initial state is 0. So that's why we are beginning with 0 here. Now the first thing, we are going to modify this counter app component so as to use the counter signal. Now the first thing we have to do is we have to remove this because this is passing its value to this counter display. So we have to remove this also because the counter display will no longer need it. It will have to read from the counter signal in order to display the value. Now next thing, we'll implement this increment function. Now instead of using this dot counter, we will now have to call the counter signal. Look at it now. When we click on this thing, it will import it from the counter signals function, counter signal function. So you see it has imported it from the counter signal file. Now we can now call the update function on it, then passing the update function. Now remember that the update function gets the current value of the signal there. So we just write, we'll grab the current value, then use it to update the value of the counter signal. Now current value and increment it. So with this, we have updated the counter signal to an increment of +1. Now look at what we did here. This update function returns a value, and the value it returns will be the next value of this counter signal. So now we grab this this current value, which holds the current value inside this counter signal, and then use it to increment it. Then now return the increment so that it becomes the newest value of this counter signal. Now let's do the same thing in the decrement method. We'll have to remove this and paste it now. But in this case, remember we are decrementing, so we have to now subtract. So we are now subtracting the current value by 1 and then return the result. Now the result will now be the next value inside this counter signal. Now here we are resetting to 0, so we will use the set method here. So we'll say counter dot set and pass 0. So this directly sets the counter value to 0, unlike these two, which uses the update to grab the current value, and whatever this function returns becomes the newest value of the counter signal, also with this decrement. Now we are done with this counter app component, so we need to go into this counter display component and see how we can display the counter signal, the value of it. Now we go into here. First thing, we are going to remove this. We are going to remove it. Now we will now import the counter signal. We now have to import the counter. First we will set it to a member variable counter, then now we will now import it. Now the counter is here, so we click on this. It imports it from the counter signal file. Now this counter now becomes a signal. See, look at it, a writable signal. Now see that we have a yellow squiggly line here. So this is just a warning telling us that the value we are rendering here is a function and should be invoked. Look at it, counter is a function and should be invoked. So if we save this like this, you see it will give us a weird string in our browser. So this is because it's rendering the object value of this counter signal. So we need to invoke it as a function in order to get the value inside it. So we put the parentheses and then save. You see we have the value of the counter signal displayed. Now when we click on the increment, you see it updates. Decrement, it updates, and then on reset it resets to 0. So you see we have successfully converted this counter app from using the traditional method in Angular to using the newest Angular signal to update the counter value. So you see this now works exactly as the traditional method. So now the thing we can take out from here is that this counter display component does not depend on this counter app component to get the counter value it will display here. So it simply grabs it from the counter signal from this file. It grabs it from there, assigns it to a member variable, and update and renders it in its template. Now whenever we click on increment, this updates. Now because this is a component and whenever we click on it, Angular runs a change detection on this component and it renders its template. Now this counter display component is also rendered. It will then now render to now display the current value in the counter signal. Now any component can use this counter display component without passing any input to it. So this counter display component kind of like is now standalone. So it reads the value from this counter signal and displays it. It doesn't need any parent component to send any value to it for it to display. Now we are going to add a show count feature to this our counter app. This show counter feature will enable us to toggle this display on and off. So when the show count is on, then this counter display will be showed, and whenever we make our increment, we can see it. But when the show count feature is off, this will no longer be displayed. Even though we click in either of these buttons, we will not see the display here. So now to do this, we will have a button here. Now this button will have a text on it reading turn on or off show count feature. Now when we click on it, like let me say turn on show count feature, now this will be displayed. But if we click on it again, turn off, then this counter display here will disappear. So this is how we are going to do it. First, we are going to create a Boolean signal where the show count flag will be held. Now this show count flag is a Boolean value. Now first, let's create the show count signal. Now let's close this. Then first we'll create a variable and call the signal function. Then we'll pass truth to it. Now this truth we are passing is that the show count feature by default or on load will be shown, that this will be shown. So that's why we are setting it to true. Then we'll save this. Now the next thing we are going to do is to add our button here. Now we'll go to the counter app component. We'll add a button to turn on or off the show count feature. Now we'll remove this reset here. We'll say turn on show count. Turn on show count. Then we'll remove this reset to toggle show count method call. Then we'll copy this. We'll copy it. Then implement the method here. Now, how do we implement it? First, we'll get the show count signal here. We'll now have to import it. Let's import it. Quick fix, add import. Now it's imported. See it here. Then now we can now update it either true or false. So in doing that, we are going to use this update function. Now inside it, we'll grab the current value. Now since we know that the current value is a Boolean value, so we use the logical NOT to toggle it on or off. So now what this does is to update this show count signal to either true or false. Now this update function here grabs the current value in the show count signal, then now flips it to the reverse of its current value. So if the current value is true, then now the value returned will be false. If the current value is false, the value now will be true. So it flips the show count value on or off, true or false. Now see here, we have the text turn on. Now we want to show this turn on when the show count value in the show count signal is off, and then vice versa, showed off when the show count feature is on. So now how do we grab the value in this show count? Now simple, we have to set a member variable here. Then now we will now read from the show count variable, from the show count signal. Now this is another function that we can use in a signal. Now this as read only returns a read-only version of this signal. You can see it from the text here. Returns a read-only version of this signal. Now read-only signals can be accessed to read their value but can be changed or using set, update, or mutate methods. So now we are returning a read-only version of this show count signal because we don't want this to be updated from the template. We are only trying to read its value so that we can flip this either on or off. So that's why we are using the read-only version of the show count signal, and this is how we grabbed the read-only version of it. Now we'll come to our template here. We'll remove this. We'll add our template binding, then call the show count, then add our conditional check, inline conditional check. Now if this is true, if the show count value is true, that means it's on, then here it should be off. If not, it should be on. Now let's save. So now you see it, we have it here, turn off, because right now by default the show count is true. So if we click on it, it will turn it off, then show us turn on. Now you can see this display here is not disappearing or reappearing. Now let's implement it. To implement it, we are going to go inside the counter display component. Now see here, we are displaying the value of the counter signal here. Now we want to make this value this being displayed here to be dependent on both the counter signal and also on the show count signal. Now we want to make it such a way that if the show count signal is off, then what is displayed here will be an empty string so that nothing will be shown. But if the value of the show count signal is on, then the value of the counter signal will be shown here. So this is how we are going to do it. We will use the computed function to implement this. First, we will remove this and you call the computed function here. We will now pass in a derivation function. Now inside this derivation function is where we will add our logic here. Now we want to show the counter value when the show count feature is true. So now we'll now use an if logic, then call the show count, then we will return the counter. So you see, if the show count value is true, then we return the value inside the counter. If not, we'll just return an empty string so that nothing will be displayed here. So with this, we have successfully added the show count feature to our application. So now if we save it, we'll still be seeing the counter value here because by default the show count is true. So you see that this code works. Now if we click on the turn off, you see that it disappears. And when we click on it again, it reappears. So you see our feature works. Also, look at the text here. Now it is off because the show count is on. So it shows us off so that it tells us that when we click on this button, it will turn it off. So you see now the text here is now on, telling us that if we click on this button, it will turn the show count feature on. Now see, it works. Now looking at what we have here, it kind of looks complex, but let me explain what happens. So when we load our application, the counter display component is rendered. Now this template, this call is made. Now being the first time it is called, it will call this derivation function. Now this if will be calculated and this show count value will be extracted so as to know whether it is true or false. Now then in doing so, it calls the show count signal. And then remember, whenever we call a signal inside a derivation function, it becomes a dependency of that signal. So now this show count signal becomes a dependency of this counter. Now remember, the value of this show count is true, so this block will be executed. Then it will return and call this counter signal, also making this counter signal a dependency of this counter. Then when it returns it, remember the initial value inside this counter signal is 0. So that's why we have 0 in the DOM when we call this here. So that's how it happens. Now let's look at what then happens when the increment decrement is called. So these three are basically the same. When we increment, change detection is run in this counter app component, and in doing so, the counter display is also rendered. Then now let's look at what happens. Now when this component is being rendered, what it means is that the template is being recalculated so as to know if anything changed, and also in doing so, this counter function is called. Then because this increment was made, look at it, updated the counter to 1, and then in doing so, it will invalidate all the dependents of this counter, which this our counter in this component is a dependent of it because initially it was called. So when this is called, it will recompute the value by calling this derivation function again. Now it will take a look at this. It is still true. It will enter here and call the value, which is in this case 1. So 1 will now be returned as a value of this signal, which will now be displayed here. That's why we have 1 here. So same happens when we decrement and then reset. Now it becomes a little tricky when we click on this turn off show count. Now when we click on this turn off show count, this show count signal is updated from true to false, and because of the event of the click on this button, this counter app component will be rendered, and in doing so, this counter display will be rendered also, which will make the template to be recalculated, and this counter call will be made. Now, because the cache of this counter is invalidated, then this derivation function will be called. It will check if show count is true. In this case, remember it is false because it was turned off. So this block will no longer be executed. It will return this value, an empty string. So now this signal will have a value of an empty string. Now, because this was no longer run, then counter ceases to become a dependency on this counter, so that when we increment and decrement, it does not invalidate any cache. Even though this component is being rendered, it does not call this again. So the display remains blank. Now if we turn it on, now this component will be rendered, and then in turning it on, remember this is called, and this show count value will be updated, making it dependent this to be recalculated, because this component will be rendered and this will be called. Then because the cache has now been invalidated, now this derivation function will be called so as to recompute the value of this. So in doing so, it will check if show count is true in this case, so this block will be executed. And in executing this block to return the value of the counter, it will call this counter signal, which will now add it back to be a dependency on this counter signal. So it will now return the value of this counter, which is 0, and then now this counter will have will be a signal whose value is 0, and then have none depend on this show count and this counter. So that's why here we have the counter being shown in this case. So this is basically how signal works with change detection in Angular. This is the end of this lesson. I hope you love this lesson, and also thank you for sticking with me to the end of this lesson. In the next videos I will release, I will talk about how to untrack dependencies, and also how to use object and arrays instead of primitives like this number and boolean we have here. Yeah, so we look at how we can use them, and also we will look at the effects API, and then we'll look at the effect signal have on push components in Angular. Thank you so much. Like and share this video, and also don't forget to subscribe for more content like this. Thank you. Bye.